welcome Greg Diamos back to Georgia Tech. So, Greg actually got his PhD from Georgia Tech, where he was looking at the development of the GPU oscillator dynamic compiler for targeting CPUs and GPUs. Then he went on to work at NVIDIA. He was looking at the microarchitecture and compiler technologies that are actually being used in the Volta GPUs today. He was also part of the whole team that invented the SIMT independent thread scheduling system. And over the past few years, he's been at Baidu at the Silicon Valley AI Research Lab, where he actually helped develop the deep speech and deep voice systems. And today he's going to be talking about how do you reach beyond human accuracy with AI data centers. So with that, Greg, the floor is yours.
Thank you for the nice introduction, and thanks everyone for coming. I'm actually curious, before we get started, where people are coming from. So how many people here are coming from maybe an ECE, electrical engineering, computer engineering background? Okay, quite a lot of people. How about computer science? Okay, so a few people. How about outside of that, maybe from other application areas? Okay, so a fair number of people. Interesting, so we've got a pretty diverse group here. I guess there's a lot of excitement around machine learning, and I've been only working in the area pretty recently, and I'm actually super excited about it. So I'm hoping in this talk I can cover a few things, actually. I'm hoping I can give some perspectives about how we got here. I can talk about some of the things that have happened recently, some of the new developments in AI and machine learning, and also maybe spend a few minutes talking about where we could go from here. What are new open areas that could lead to future improvements in performance for products that could actually be beneficial to people, but also new research topics that are kind of getting at some of the fundamental issues in building faster computers and in building algorithms that can learn. So one of the things that happened to me recently was that I became a father. I had a baby earlier this year, and one of the things that I love the most about being a parent is the ability to teach stories or tell stories to kids. And one of my favorite stories in the world comes in this format, in the book of Science and Technology. So there's some really amazing stories in here. Like the story of the origin of species. We have interesting characters who navigate the high seas, circumnavigate the globe, discover weird and exotic creatures, and learn insights about the basic building blocks of life. The story of electricity and magnetism, this is something that I learned a lot about in the ECU department. But we have, again, interesting characters performing cool experiments, using mathematical machinery, and uncovering invisible forces that allow us to connect all of our world together, bring the entire globe together, give us cell phones, and allow us to communicate with each other. Or the story of the age of the universe, where we can actually map back to the very beginning what the few moments in the very beginning of the universe look like. So there's some really amazing stories in here, and one of the things that I'm super excited about as a parent is teaching these stories to my kids. But there's one of the other good things about this book, the book of Science and Technology, is that it's constantly being written, some of it by people here. And one of the maybe most interesting stories of all, the story of human intelligence, is still in progress. We still haven't figured this one out yet. There are a lot of unanswered questions here. But I thought it might actually be useful in this talk to go through, if we wanted to write the history of human intelligence or the story of human intelligence today, what are some of the pages that you might find in that book? What are some of the steps that people have taken along the way that have gotten us to where we are today? I think this will inform where we're going to go next. So I want to begin with a question. It begins in kind of an unrelated place. It begins with this question. So thinking, landmarks people are usually familiar with at Georgia Tech, the Campanile. We're here in the Nano building. Just ask a question to you guys. If we wanted to measure the distance from the Campanile to the Nano building to arbitrary precision, but we had to use a really inaccurate tool. We had to use the odometer on the Rambling Wreck. How could we do that? Does anybody have any idea? Sorry, could you say that a little louder?
You could hire a accelerator to walk distance with something similar to that circumference.
So you could hire an intern to do this. I get a measurement. What if I wanted it to be super precise? What if my granularity on the first measurement was in meters and I really wanted it in centimeters? What could I do? There you go. Do it 1,000,000 times. I like that answer. So there's a long history of observing that empirical statistics, such as averages, get better with more trials. So maybe 1,000,000 trials would be, might expect it to be more precise than a single trial. And in fact, this phenomenon actually leads to convergence. So we actually see that it converges to the right answer, assuming it's not biased, as the number of trials approaches infinity, if we have 1,000,000 trials. This is so-called the law of weak large numbers. So it turns out that our story of understanding human intelligence starts here. And it started, so this kind of observation has been used to great success in statistics by many people for hundreds of years. But recently people started asking a different kind of question that's related. They started asking, what can we say about a specific number of trials? Maybe I don't want to walk back and forth 1,000,000 times. I don't want my intern to get tired. Or I don't want to take all summer doing this. I'd like to figure out exactly how long I'm going to expect to do this. So Hermann Chernoff worked on this problem in the 50s, maybe a little bit earlier than that, and tried to answer this question. And this led to what's known as the Chernoff bound. So this is a more specific estimate for specific types of distributions of exactly how many times you're going to have to walk back and forth. This led to the foundations of machine learning. So this led to multiple lines of work. One of them was done by Leslie Valiant called The Theory of the Learnable. This was done in the 80s. It's worth noting that this kind of approach has been seen before. There are three main differences that really set this apart from prior work, mostly in statistics. Michael Kern summarized this pretty well in his thesis. I'm just going to repeat it here. So the biggest difference between this line of work trying to discover learning algorithms and prior work is that we're allowing approximations here. So in pattern recognition literature, you might be searching for the right function that's going to solve some problem, but you might be thinking about it from an exact perspective. You might want the exactly right function. In this perspective, we're allowing relaxation, so we're allowing approximations. We're allowing 99.9% accuracy is good enough. And this is with us today in all of the accuracy numbers that we see in machine learning algorithms. We never get, you got the right answer, you got 50% accuracy or 90% accuracy. One of the biggest differences here is that it added a component of computational efficiency. So we now don't just care that we get the right answer in an infinite number of trials. We'd like to say something about exactly how many trials, how efficient is this going to be in an algorithm's perspective. And finally, we'd like algorithms to be general. We'd really like to find learning algorithms that can solve not just a task in vision, but can solve a wide range of very diverse tasks. So this is maybe a starting point, and I think this set off a lot of work that was trying to discover algorithms with these characteristics, and it frames a lot of modern machine learning. We also saw some successes building deep neural networks. I know a lot of people, when they're doing histories of machine learning, they're going to focus a lot on deep nets. I'm focusing more on statistics here. But people did build a lot of interesting things with deep nets. So a long series of work leading up to some very interesting results around the mid-90s where a number of people, I think it's worth noting the last author on here, Vladimir Vapnik, who doesn't get a lot of attention here, but defined a lot of the frameworks that you use to justify the designs of these kinds of deep neural networks. We ended up with our conv2D primitive that we still use today, and it was trained using backpropagation to solve some interesting problems, like recognizing handwritten digits on letters. So this was there. We had some cool theoretical results. So we learned that deep neural networks are universal approximators. That means that they can represent any bounded continuous function to an arbitrary error rate. They can also represent any Boolean function. So that's a pretty big class of different functions. If I'm searching for a solution to my problem, it's maybe very highly likely that it's in that set of functions. But we have a problem. We have to set the weights to the right values, and that should be pretty easy, right? And this is where we run into problems that loss surfaces of deep nets, there have been prior theoretical results on this showing that if you have a deep neural network with, for example, 1 million weights in it, you have an exponential number in 1 million, which is a giant number, critical points in the size of the net, saddle points or local minima. So it might be a really challenging optimization problem. We're searching for a needle in a haystack. And maybe that's the worst case, but what about in practice? The figure here is from ResNet. This is a visualization of the loss surface of ResNet, and you can see that the losses of real nets can be pretty bad. I actually really like this quote from Leslie Valiant, who founder of PAC Learning, because sometimes in machine learning we feel like we're not making any progress. But I like this quote. So in 1994 he said, "Humans can perform significant tasks of scene recognition in a few hundred milliseconds, tasks that no one can perform by computer, no one knows how to perform by computer, in principle, in any amount of time." So that was kind of, optimism, but then recognizing that we're running into some, really significant limitations here. And it wasn't really clear to see, what the path forward from this is. And I remember when I was in school, this is what things look like. We had all of these prior results that seemed promising, but it's really hard to overcome some of these hard problems here. So it's not really clear how to apply this. In the meantime, other things happened. We built some really fast computers. This here is a picture of John Nichols. John was probably not really well known, but probably one of the fathers of GPU computing. I think of, if you think of the story of how we got GPU computing, it was basically John, Ian Buck, and going to the CEO of NVIDIA and basically saying, this argument, if we build it, they will come. We have no idea who's going to use this thing, but if we build it, they will come. Please pay. Please pay for this. And it was actually kind of interesting to be at NVIDIA during this time. I did a bunch of internships at NVIDIA, and my salary was definitely paid by this this kind of belief that if we build it, they will come. We didn't really know who they were at that time, and we had a lot of ideas, but it was kind of interesting to see that a lot of the ones that we thought were good bets didn't really pan out. And I remember deep learning was something like 11 on like a list of 20 different things that would be great if only we could get them to work. So sometimes it's good to dream big, and I think I agree with this statement here that if I had a field of dreams, it would be filled with racks of GPUs at this time and today. Okay, and so luckily they did come. So this, probably everybody is aware of this result, AlexNet. Basically taking the same ConvNet approach, applying it to a large scale, significant scene recognition task, maybe giving us some hope that even these really hard problems that seem like they're impossible at one point by experts in the field, we can make progress on them. And if we look back 50 years ago, understanding human intelligence might seem insurmountable. It still might seem insurmountable today, but we've made some progress. I'm hopeful that we can continue to do that. So this really set off people getting excited about this again. This is weird. These things are actually working. I think this might sum up, like, people still argue about why this happened or what was the thing that was really essential here. People also still argue about why critical points, the exponential number of critical points, aren't a problem here. I don't think there's a consensus about this, but I think that this result gives us the most intuition out of all the results that are out there. So the idea here is that if you analyze the loss surfaces of deep neural networks and you make them big, so if you have a small neural network, you see this pretty wide distribution of losses. The best minima are way better than the worst minima. But if you make the network really big and you just train it over and over and over again, and you find different minima every time, the difference in performance between those minima shrinks. This distribution tightens as you get bigger networks. And so maybe we didn't need to find the global minimum. Maybe there are a lot of really good minimum in there. And maybe this is the thing that we're missing. It's still intractable, but maybe we didn't have to solve as hard of a problem as we thought that we did. And so today, you see successes everywhere. So I can't fit them all onto one slide. I think Andrew Ng coined this phrase, AI is like electricity, which I think summarizes it, that in the Industrial Revolution, we figured out how to apply electricity to basically every industry. If you look around, you can't find an industry that doesn't use something powered by electricity. AI seems like it's general purpose like that you can probably apply it to absolutely every single industry and it will be useful in every single case. So I'm going to call out some examples that we've seen that are useful, like object detection, speech recognition, machine translation, medical imaging, discrete optimization problems like Go, great, and even things that require generation of high-dimensional data, like generating images or generating speech, work very well today. And I can't fit all the stuff on one slide. Okay. So that was a little bit of history, how we got here. I want to focus on one piece of this. I said at the very beginning that one of the reasons why this is working so well is that we're making an assumption that we can learn from data. We're using statistical effects to drive the learning process. The reason why we have a lot of confidence about things like neural networks actually finding good solutions out of this vast space of possible solutions is that we're relying on statistical laws to rule out possibilities that aren't interesting, that aren't consistent with the data. And so I want to zoom in on this in a little bit more detail. I think this is absolutely very important. So we come away with this kind of takeaway that there's no data like more data. If we want to solve a really difficult learning problem or a really difficult problem that maybe a person can do really well, but it's really hard to think about an algorithm, like writing down an algorithm by hand that can do this really well, maybe all we need is just a pile of data. So there have been a lot of results where people have tried this out and it's worked out pretty well. This has led some people to make some pretty bold claims, like, if we try out a whole bunch of different learning algorithms, it's hard to say, what detail about what algorithm on what data set is the most important thing, but consistently across all algorithms, we can see that more data improves performance. And so there's no consistently best learner across diverse problems and diverse algorithms and different data sizes. So maybe we shouldn't be thinking about spending so much time inventing new algorithms. Maybe we should fire everybody and just buy a lot of data. So this is a paper that was published by Banco and Brill. This is a quote from Brill that we should fire everybody and spend the money on data. So we're going to get back a little bit more technical here. I'm going to talk a little bit about, all right, now, if we want more data, how much data? This is a very important question if you're going to be writing a check for it. So what does theory tell us? So I mentioned in the very beginning, PAC Learning. There are a bunch of other theoretical results here that are going to give us bounds on the error given how much data we have. One thing that's interesting here is that there are multiple lines of work here. I'm mentioning two well-known ones. One is Rademacher complexity, one is VC dimension. You don't have to understand the details of this, but the point here is that they all have a term where the error is going to decrease as a power law of the dataset size. So M here is the dataset size. Power law just means proportional. And so here the proportion is, we don't really know what that ln 1 over delta is, or that log m over d is, but there's an m to the minus 0.5 in here somewhere. Okay, and so some of my colleagues using these kinds of theoretical results as justification said, well, maybe it's hard to say theoretically what the characteristics of real applications are. Real applications have a whole bunch of stuff going on in them, like a machine translation example or a speech recognition example. Those are really hard to analyze theoretically because we have to know things about the distributions of data, we have to know things about the models, we have to know things about how the optimization algorithms are working. That's really hard, but because the main principle that we're relying on here is this, these bounds, maybe we'd expect the real behavior to follow a form that's consistent with these bounds. So we can model error as a power law. So A times m to the b plus gamma, or alpha m to the beta plus gamma. Alpha and gamma are constants. They have dimensions, so that means that they're going to be different scales for different problems. Like you'd get potentially very different results for speech recognition than machine translation because one uses word error rate and the other one uses something like BLE as error metrics. But you might imagine that beta would be dimensionless. And what does beta actually represent here? It represents the reduction in error with more data. So as you add more data to the problem, proportionally, how much of a reduction in error do you get? And so combining this with other theoretical results, we get this kind of a format here that you'd expect models to be in a small data regime. They eventually transition into this regime dominated by power law scaling. And then eventually, there is such a thing as enough data. If you solve your problem, it's enough data. So you'd expect that eventually you hit some lower bound on the error that you could possibly achieve. We've never actually seen this for a real problem, like a machine translation or a speech recognition or image recognition kind of problem. But you can show it for toy examples and the theory would predict that it exists. So armed with this, let's look at what we see in practice. So this is scaling according to the same model of image recognition, which is well known. So on the left here, you're seeing the learning curves for different metrics for ResNet trained on ImageNet. So as you add more data, as you add more of the ImageNet data set to the training system, how is the error improving? And here, less is more, so this is error, so down is better. We're looking on log scales also is worth mentioning. So we see regardless of what metric you can pick cross entropy, you can pick top 1, you can pick top 5. They improve differently, but once they improve in a way that's very consistent with this theory. That as you get more data, you're going to expect to get proportional reduction in error. So everything scales with data, and we can actually know pretty precisely how much data is going to help us. Looking to the right of the figure here, we can also look at, well, how much bigger do the models need to be? We know also that if I have a 1 hidden unit neural network, it's not going to be able to do ImageNet. I need probably more capacity as I have more data, or I need a bigger neural network as I have more data to absorb all of the information in that data. So how does it actually scale? So it can also be modeled as a power law. So we're looking at growth of about square root. So as the data set grows by a factor of 10, we're looking at a square root of 10 kind of increase in the model size needed to fit it well. Okay, so we can look at this across different applications. We see the same behavior across many applications. The exponents are different. So we're looking at language modeling here. On the left, it's comparing a bunch of different architectures. So RNNs are common architectures. You can see they all, different variants of RNNs all have the same exponents, so they improve the same as you add more data. Architecture does help, so if you have a better neural network architecture, it's basically going to shift the whole thing down, give you something like a constant factor reduction in error. So it's still a good way of adding additional accuracy, but there's no data like more data. All applications, all models are going to benefit from more data. You can see somewhat similar scaling results for the model size. We can also predict pretty accurately how much bigger models are going to need to be to absorb bigger data sets. Okay, and so I'm not going to show you all the results here, but we can repeat this over and over again for a bunch of different applications. And we can come up with some pretty interesting observations. So here I'm showing 5, language, 2 from language modeling, 1 machine translation, then speech recognition and image classification. These are pretty well-known examples of deep learning applications that are working pretty well today. And so we can look at how fast do they scale with data, and how much bigger do the models need to be to absorb all that data. So we can look at beta G, it's describing scaling with data, and beta P, describing scaling of the model size with data. So for beta G, less is more. You want this to be as small as possible. Tasks that have smaller beta G get better faster with more data. And so we can actually see that you get an ordering over tasks, where tasks in language scale slower than tasks in speech and vision. And it's probably not an accident that we saw results come out kind of in this order, that we saw first results in image recognition, speech recognition was pretty close behind it. Language modeling, machine translation, tasks in natural language are generally considered to be harder by the communities than these other domains. And so this gives us some intuition about why this is happening. We need relatively more data to solve problems or to reduce error rates in language domains than we do in speech and vision. So this is pretty consistent with just people's experience of how hard these problems have been. So this gives us actually kind of an interesting way of organizing the space. You can record this kind of scaling relationship for any application, and we could use this to produce a hierarchy kind of similar to notions of time and space complexity. In computational linguistics, we have the Chomsky hierarchy. These are useful for guiding relative difficulty of problems. Are you working on a toy problem, or are you working on one of the hardest problems? It'd probably be a good thing if you knew that. If you measure beta G and compare it to some of these example data points, you can see whether you're working on a pretty easy problem. It's not going to take that much data. You'll make progress relatively rapidly, or you're going to need a massive amount of data to get an incremental improvement.
So do these insights only work for deep neural nets, or is this like across learning algorithms? You started with kind of non-deep nets and we're just talking generally about...
Yeah, so I think the theoretical results that provide bounds are going to apply to all learning algorithms that adopt the same framework. There are some assumptions in the framework, so like and these are the assumptions that we almost always make, like we have training, we have validation sets, we're drawing independently from them, we're making some assumptions about distributions, we're making some assumptions about the families of models. They're very consistently used in machine learning. I think this is going to apply to quite a lot of machine learning. It's also worth noting that these are all empirical results, and so there's potentially a difference between bounds, which you get in theory, and then what you observe in practice. I don't think it's a foregone conclusion that you'll always see this for every learning algorithm. We only have the data that we have.
Isn't this just a function of, as you get more data, the distributions in your training set represent the actual distributions more accurately?
So the question is, isn't this just saying that as you get more data, then the distributions in your training set are representing the real distribution better? I think it's possible. Yeah, I think that I think there's also questions of difficulty here. So I think you will definitely get more accurate representations of the distributions in your data with more data. I think the interesting thing here is their relative rate. If you go back to simpler theoretical models, you can show examples of toy problems that would have different, there's maybe like a loose analogy to something called sample complexity here. So you can certainly think of problems with different sample complexities. And in this framework, what you'd see is that problems with different sample complexities would have different relative improvements with more data. So I think it's consistent with what you just said. I think that still having this kind of way of measuring relative difficulty of problem is useful for realistic problems. Okay, let's keep going. So if one way of improving on results that we already have is just adding more data, If we wanted to make meaningful improvements in all of these different areas, how much data would it cost? So we have a scaling model. We can use it to project how much more data do we need. So we tried to go through this exercise and just write down some of the new data set sizes that we'd want in these different areas. If you wanted to do, we went off and asked experts in these areas what they would consider to be a meaningful improvement over existing results, many of which are already approaching human accuracy or at human accuracy. What would they be? And so we came up with these desired targets for each of these areas. Sometimes they're cutting error rates in half, sometimes they're going more aggressive. And you could look at how much bigger these data sets are than the ones that we have. So for speech and vision, they're not that much bigger. They're maybe an order of magnitude bigger, maybe about 10x bigger than the ones that we currently have. But the ones in language are quite a lot bigger. So they're maybe between 100 times and 1,000 times bigger than the ones that we currently have. There's also a point that comes out here that's a systems question, which is what are the I/O requirements of training, like from the training data set perspective? So these are challenge problems. These would significantly extend the state of the art. All of these are under 100 terabytes. So I could probably fit these on like an SSD that was very dense with a lot of memory, if I was very aggressive in my SSD design. So this is not hundreds of petabytes. We can also look at the computational requirements. So here we're taking those data requirements together with the model projection requirements to say how big will models need to be, and then what are the computational requirements. Again, for speech and vision, they're manageable. You could train in about 3 months on a single accelerator one of these models, if only you could fit it. And you probably could fit it if you're careful. So they might take a little bit under 1 billion parameters. But in language processing, you need way more. You need, I'm going to throw out the character language model example here because it's just so computationally expensive, it's probably not worth doing. But if you look at word language models and machine translation, you still need tens of billions of parameters. This is going to be in the range of tens to hundreds of gigabytes of memory. If you tried running this on a single accelerator, it would take you between 50 and 10,000 years, depending on which one of these problems you're trying. And that's assuming you're getting peak efficiency. So it's not really feasible to run these things on computers that we have today. And getting a, maybe 1,000x improvement in throughput for a single accelerator, I would love it if we could do that. I think people are going to come back and tell me that's hard. Okay, so what can we do? So I'm going to propose we should build some giant AI data centers. So what does that mean? So actually, has anybody here actually seen a data center? Seen like a couple people here. What's the right analogy for like seeing a data center? Like what other thing that people have built is the right analogy for a data center? Anybody want to? Sorry, something in the back? A what? A what, sorry? A refrigerator. A giant refrigerator. I was going to say like an oil refinery or like a power plant or something. Some of the data centers I've seen are about 100 megawatts. If you think about a 100 megawatt power plant, kind of gives you the right idea. Smoke billowing into the air, having a lake to sink the heat into, kind of a thing. So these are giant computers. We think of supercomputers as being big. Data centers are bigger than that. But we design them differently. We don't really design them to run machine learning today. So we usually focus on scalability. We want to support all of the internet users. We want to give email, chat, Facebook to everybody in the world. So a lot of jobs, we usually run general purpose programming languages. We'll write high-level languages like C, Java, JavaScript, and we'll run them on general purpose processors like CPUs. CPUs got way faster. At the same time we were building faster computers, CPUs also got faster, but I think we can do better than that for these workloads. So, and I think a lot of the main ideas here have analogies to what people have been building in supercomputers. So sometimes called this high performance computing. Instead of scalability, the focus is on capability. So like the speed of a single task. How good is my single task? Jobs can be a lot bigger. Rather than running a lot of jobs on one machine, I'm going to run one giant job that's going to take up quite a lot of machines, maybe thousands or tens of thousands of processors. And I'm going to be more open to embracing special purpose accelerations. So things like domain-specific accelerators, GPUs were early examples of this. We have moved on from that. And I'll program them not with general purpose languages like C or Java or JavaScript. I'm going to program them with domain-specific languages. And we've seen deep learning frameworks emerge. So in order to build this, in order to build a data center that's any good, we need to be able to measure progress. So one project that I like that's recently trying to do this is called MLPerf. The idea behind MLPerf is to be like spec for ML. Do most people know what spec is? Kind of, sort of, maybe. Spec was a wildly successful benchmark introduced in the 80s. It went hand in hand with many of the large performance improvements in general purpose computers between the 80s and today. If you'd like to learn more, there's a website, mlperf.org. The idea here is just to define important machine learning tasks like speech-to-text, translation, recommendation, sentiment analysis, object detection, and provide high-quality reference implementations so you can measure how good your new system is at these important tasks. I mentioned specialized accelerators. What are some of the trends that are going on and being added into specialized accelerators? I think there are three really big ones. There's a lot of other ones, but I think these are really worth mentioning. That in the past, we used to talk about parallel computing, like vector computation, building SIMD machines like GPUs. Today, we're building processors that do linear algebra operations, that do matrix vector operations efficiently. By moving to this higher level of abstraction, we throw away a lot of general purpose programmability, but we gain efficiency. We also need way less precision for these algorithms than we thought that we did for scientific computing. I'm not actually sure if we need that much precision for scientific computing, but it was cheap to build at the time, so why not? Maybe people are starting to revisit that now. But certainly for neural networks, for deep learning in particular, you can get away with lower precision than double precision for sure. Pretty much everyone accepts that you should use single precision. I think there's been a fair amount of work showing you can do better than that using mixed precision. You can go even lower for some kinds of aggressive inference or some kinds of modifications to the training algorithms. And there's also a point here that the biological analogies here I'm not a huge fan of, but for one reason or another, it seems like a lot of the weights in neural networks are redundant. And you can get rid of them, and it doesn't hurt accuracy very much. And if you do that, then you can spend way less compute, way less energy getting to the same answer. So sparse models for the same size usually beat dense models. So all these trends can be leveraged when you're building an accelerator. If you're only going to run workloads that look like this, you can be a lot more efficient than if you want to be general purpose. We also want to scale out. So one thing that you might see in maybe announcements about people building hardware designs for machine learning is that they're moving towards larger scale units of computation. So we've seen a number of things that are called pods. So these are tightly integrated collections of processors that are specialized for machine learning training or inference. The idea here is that data movement's expensive. We want things to be local. We don't want to be sending things all the way across one side of the data center to the other. When they're directly communicating, we want to put them right next to each other so we don't have to spend as much energy sending data. So we see these things that are called like accelerator pods. I think the TPU pod from Google is a well-known example of this. People in practice who deploy GPUs also build GPU pods. There's another trend that's worth mentioning here that I'm just going to call large batch training, where if you can, like one of the criticisms of a lot of these kinds of algorithms is that maybe you get a fair amount of parallelism from a neural network, but is that really enough to keep 1,000 machines or 10,000 machines busy? Probably not. So one of the things that's common to do here is use something called data parallelism, where you just train on a bunch of different samples independently and then periodically synchronize things. This has been criticized in a number of different ways for a long time, that this isn't going to go forever. If you just, maybe scaling from one sample at a time to 2 samples at a time is okay, but going to 10,000 or 1,000,000 is probably not. Exactly where does that end, people still debate about. One of the interesting trends is that probably through notions with scale, like this probably works better for bigger data sets and bigger models than for small ones. And also by tweaking some of the algorithms, you can get much bigger amounts of data parallelism through what people call large batch training than what people used to believe. So the combination of all of these things is probably exposing the opportunity to run some of these algorithms on a lot of machines at once. Okay. And so we can build all of these components. We can build specialized accelerators. We can measure our progress. We can scale out to a lot of different machines. But then we have this problem of how do I program it? And this is actually probably a triumph. Like I remember when I was in school, we used to talk about programming models that would be kind of like this, and I never really believed that we would ever end up building them. Like I think after working on them for a while, the conclusion was, yeah, they could be way more efficient, but they only apply to kind of graphs of dense linear algebra. Who wants that? Some people do, but it's not Java programmers. Turns out deep neural networks want that. And so we have a whole bunch of frameworks that express computation as compute graphs plus auto differentiation. On top, we're building that on top of these libraries that are optimized implementations of these things. There are, for things that don't fit, we can have domain-specific languages, like mapping directly from those graphs into code generation for accelerators. We also have general-purpose parallel languages like CUDA, OpenCL, OpenMP that allow us to write relatively high-level parallel programs. So these gives us ways to get onto accelerators. We put these together into a pod, and then we can build accelerators through multiple different approaches. We can use GPUs, we can use these kind of array-based processors, we can do processing in memory, we can have specialized data paths, specialized communication paths. There's a lot of opportunity for innovation at these different levels. But it's kind of interesting that we can end up with something that's fairly high level for this diverse set of applications. Like if you look at the applications at the top, you're really cross-cutting. Like this is speech, vision, text, search, recommendation. Quite a lot of the important workloads that we run at scale in data centers can be mapped onto something that seems fairly constrained in special purpose. I mean, if you look back historically, the closest analogies here are to things like like this is like running a giant distributed computation on MATLAB. And I think it's kind of strange, maybe that so many different things can be supported on something that's special purpose. But this is kind of where we are today. Okay, so we talked about how we got here. We talked about the importance of data, like the role that data has played in how we got here. We talked about, as we demand further improvements in performance, we're going to need more data. That's going to demand even faster, even bigger computers. We might have to look to much bigger computers to be able to solve some of these problems. What are other open problems? So clearly, the whole book of human intelligence hasn't been written yet. There are a whole bunch of pages that haven't been written yet. What might some of them look like? So I'm going to spend a little bit of time here just focusing on things that are at the edge, like things that are problems we do not know how to solve right now. We do not know the answers to these questions, and maybe some of the people here can help write some of these pages. So one of them is definitely even faster computers. I think the argument of build it and they will come still applies here. I've been trying to think about what does exactly that mean. So I think I'd probably express it in this way. Build a computer that gets 20 teraops per watt at the whole application level, or 5 petaflops per second throughput in a GPU form factor. These are kind of equivalent statements. And then build it in a way that it scales out transparently to the biggest data centers that we have, around 100,000 processors, around 100 megawatts. And make it simple to program. Especially support those large models that we predict that we're going to need. So, high bandwidth memory has a roadmap. I don't think it's going to get us to hundreds of gigabytes anytime soon in single accelerators. How can we support that transparently in a way that doesn't drop our efficiency down to 0? And we also, as we're doing more co-design work, we're exposing all of these different trade-offs. So we've seen precision, we've seen sparsity, we've seen architecture, model size. That's really complicated. Throwing that to a designer, we see some people who are willing to bend over backwards and do a 3-month design study and take ImageNet and produce MobileNet, kind of like compiling ImageNet to something that runs on a mobile platform. We've seen this in a bunch of areas. It would be great if we could automate that. That's a ton of work. That's really hard. So, how many of these trade-offs can we do automatically? Is there like an analogy of a compiler for a machine learning algorithm to a hardware platform? And we want to support multiple hardware platforms. We want data centers. We also want edge devices. It'd be great if we don't have to do that huge design study in both cases. There's another really important trend that I just have to mention here. AI, like electricity, applies to pretty much everything. We use a ton of heuristics when we build computer systems, every single component of it, from physical design, in architecture, all the different units we build, at the programming system level, in libraries, auto-tuning. It's everywhere. What can we learn from learning algorithms? We have these really powerful tools that allow us to develop better heuristics to solve problems approximately. Don't have to get the exact solution, just give me the best solution you can find. I bet you can apply machine learning to every single one of these. Okay. It's worth asking this question. We saw that we get scaling with data. Where is the data? What data resources do we have kind of as a society that we can leverage to solve new problems? Oftentimes what I've noticed is that in order to leverage a data set, you have to frame the problem correctly. In speech recognition, when we were working on speech recognition, we used to frame the problem as audio on an input using these weird features called MFCCs, outputting into something called phoneme probabilities. It's kind of a weird representation. Getting data in that representation was really hard. Reframing the problem so that we had audio on one end and text on the other end opened up the door to a lot more data. I think it's worth asking, where is the data that we've already collected that's already lying around? And how can we set up a problem in a way that a learning algorithm could actually take advantage of it? Just to give an example, if we look at what this looks like in Baidu, we have something called the Big Data Platform, which ingests about 10 petabytes a day of query data as people use services, all sorts of different services. And a lot of this is just going through the system. We've leveraged a whole bunch of things like making speech recognition better, making recommendation better using data. This is like a fire hose. There's way more in here than what we're using. There are probably a lot more opportunities to define new tasks and solve new problems. And I think this exists way. Go ahead.
So I have a philosophical question here for you. So when you're talking about data here, this is all very structured, labeled data, right? So there is a lot of data out there, but it's not in that format. So I guess what are your thoughts for learning algorithms, learning from data that's not labeled or structured, whatever, like however you want to say?
Yeah, so how do we handle data that's not labeled? I think this plays into a bunch of things. I'll mention a couple in a second, but one of them that's really important is that creative reframing of the problem. So when we looked at speech recognition, it was really hard to get those phoneme labels. It was really easy to get text. Oftentimes you can invert the problem. You can just say, here's a bunch of books, read those books. And that's way easier than asking people to listen to a bunch of audio recordings and then transcribe things accurately. So the creative reframing of the problem, I think, is an essential component. Let's see some other things. All right, so clearly it's important if we could have algorithms that could learn faster with even less data. So we have theoretical results, we have empirical results about how different applications scale with data, but what are the factors for real applications? I think it's really hard to go from abstract notions like VC dimension to speech recognition. Tying these things together in simpler ways would be very valuable. I think theoretical work could do this. I think empirical work could also, maybe we have simple ways of measuring the characteristics of a problem that lead to better or worse scaling. And if we know what the characteristics are, maybe we can control them. There's an open question here. Everything we studied was supervised learning. So I think there's an open question. How do unsupervised learning and reinforcement learning framings of the same problem scale? I think there's intuition that some of these things need more data, more compute. We were able to brute force Go, but we needed a lot of compute. Is that it? Is unsupervised learning just a matter of scale? Do we just need a big enough computer? I think these are open questions. I think we have some tools now. You could look at these things theoretically or empirically. Clearly, we know prior domain information helps. Architecture matters. ResNet is way better than AlexNet. But it seems kind of like a weird way of specifying prior information in an architecture of a neural network. Maybe there's a simpler way of doing it. When I'm changing the architecture of a neural network, I'm changing the prior information, but I'm also changing the computational characteristics. And these things are coupled together in a really nasty way that maybe I've seen a whole bunch of examples of, I found this more accurate version of this algorithm, but now I have this annoying computational problem if I can't deploy it because it's too expensive. Could we decouple these things somehow? Doesn't seem like there should be a fundamental reason why they're coupled. Also, we have this learning setting. I went back to like, where do these kinds of results apply? They apply in the setting where we get a bunch of training data, we hit go, we train a model on it, we produce a model, we're done. If you wanted to do something more than that, like handle multiple tasks, take that model and then apply it to the next problem, and then the next problem, and then the next problem. They don't really fit into this framework. And so we don't really have good ways of predicting when this is going to work, when this isn't going to work. People have gotten it to work in practice in some cases, but what can we say about that generally? Can we have frameworks that allow us to know when this is going to work and when this isn't going to work, or to automate it? And so there's a bunch of different pieces. I think there's a better together story. There's a whole bunch of different knowledge sources, like a bunch of information that we can use to realize performance improvements in algorithms. And I think these things are better together. So just listing out a few of them. We can get information from data. We've seen that. If you frame the problem correctly, we've seen as you add different losses to new problems or to the same problem that can improve accuracies. We can add prior information in setting up the problem or in the architecture. We've got a bunch of information lying around in trained models. Like, people are spending an enormous amount of computational resources just training models, and they're just kind of just sitting off to the side. There's a lot of information in those models. Do we really need to like restart from the beginning to get back that information? And clearly also we get information from interactions with the environment through sensor data or through simulations. Like, people have already written down generative models by hand for different domains. So can learning systems take advantage of all of these different data sources and put them together? Can we handle enormous data sets on giant computers? Possibly think about multiple tasks at the same time rather than single tasks, leveraging information, similarities between tasks. Do we really have to write down architectures by hand, or can we search over them? If we have trained models, do we really have to retrain them from scratch? Can we just extract the information using techniques like knowledge distillation? And yeah, in terms of simulation, information from the environment, I wonder if we can encode it in generative models. So I think if we put a lot of these things together and got these components to work together, we could solve much harder problems with less data, less new data. All right, and these are pretty big questions. So, in the book of Understanding Human Intelligence, there are some really big open questions. There's a whole bunch of stuff we don't know. Here are some interesting ones. So, does human learning follow the same kind of scaling laws? Is statistics enough to explain human learning? Probably not the whole story, but be interesting to ask this question. There's a whole bunch of things we know that exist in people that we have no idea how they play or interact with algorithms like sleep or priming. There's a whole bunch of things. Do algorithms or should learning algorithms exploit hierarchy? I think this is an open question in multiple domains. We see hierarchy in neural network architectures, but learning doesn't really happen hierarchically. We're kind of just throwing samples at this thing. We're not trying to build on concepts. And how do we put all the pieces together so that they work together? They can solve multiple tasks over an entire life, like the brain can. All right, so reached the end. So we've seen some information about how we got here, the story of human intelligence, how it's a work in progress. We've seen that there's no data like more data. Data alone is probably enough to let us reach beyond human accuracy in many tasks. We've seen that some tasks require computational resources that are beyond single machines, that we might need to scale to much larger machines to be able to attack them. And we've taken a look at some of the open problems, some of the questions that maybe could be potential future work. But we better get on it because our little learners are waiting to read the rest of the story, and I hope that maybe by the time my son gets to maybe 10 or 15, I can actually tell him some of the answers here. Thanks.
Questions?
Sure. So the question was about, what are the implications of some of these approaches on maybe network topologies or network designs? Clearly, if we were trying to exchange the data all the time between nodes, then this could be really inefficient. This is a really important question. I mean, I think that so I think you could have potentially different answers depending on what level of the system you look at. So if you're looking at the data center scale, you're probably going to get a different result than at the pod scale, than at the accelerator scale. There's a whole bunch to say about this. There's one non-intuitive thing I want to say about this. So why do people have pods? Pods are kind of like a weird concept. They're like this, like why don't we have pods in supercomputers? We don't have pods in supercomputers because people think kind of holistically about the network. What is the right topology for the whole system? In data centers, you still have this constraint that's left over from this kind of focus, that the focus is on many jobs, many users, supporting many people with the same infrastructure. So scheduling is usually approached very differently. Scheduling, coming from a hyperscale perspective, is take a job and spread it out as much as possible. I like this because I get load balancing and I get fault tolerance. That's really bad for locality. And so in order to recover locality, people start thinking about designs of maybe a handful, maybe up to 100 accelerators together, and thinking about what does the network topology of that unit look like. And then in the context of a whole data center, I can allocate individual units of this size according to the approach that I already know about. So it's kind of a weird artifact of how we got here, but it actually ends up being an important design constraint. I think that's something that will end up impacting network topologies that might not be very obvious. Yeah, other things here, I mean, I think I think there's a lot to do here still in getting data parallelism to work at scale. I mentioned large batch training as a trend. The extension of this trend is everything just looks like a LinPack, and then it doesn't matter that much. I don't know if that's right or not. So I think someone needs to go out and answer, is that right or not?
More questions? We have time for one more. All right, okay, so let's thank our speaker again. Okay, sorry. Hi.
Just going back to that curve that you showed with respect to the beta G versus data sizes. So this was mostly
this one?
with the, this one.
Okay.
So basically there is a constant factor beta which you are trying to estimate based on a certain learning algorithm, and the whole idea behind building data centers or more faster ways to do it is because you feel like you need more data to solve a particular task and also bigger models. But is there maybe some different kind of learning algorithms that we can use that can maybe improve the beta value altogether?
Right, so the question is, can we improve beta G, the rate, can we learn faster with more data? I think it's an open question. As part of this work, if you want to look at more details, there's an archive paper here. But let me just summarize a couple of things. We tried to think about what's going to change this. If we can change it, we can control it. And that would be great, because then we could learn faster with more data. We tried a whole bunch of things. One of the most common things that I think people believe that changes this is architecture. And maybe like very major changes in architecture, like completely different representation classes, is going to do something here. But we tried all the stuff that people are commonly using across 5 different applications. And what architecture does here is it's like adding prior information. It's like you start from a better place. You do get an improvement in accuracy, but the relative improvement with more data isn't there. It doesn't make hard tasks any easier.